Hello, I'm Junghoon. I'm going to talk about our paper, ProFeat, Unsupervised Image Clustering via Progressive Feature Refinement. The unsupervised image clustering task is to group images into semantically similar clusters without label. Unsupervised image clustering involves representation learning and clustering. Representation learning is the task of the learning how to map images to feature, and clustering is the task of the grouping feature into semantically similar clusters. Recent unsupervised image clustering studies have focused on the simultaneous training of the representation learning and clustering. One of the research directions is an iterative refinement method using intermediate clustering result. However, this method has the following problem. The problem is that clustering using full representation is inaccurate. Inaccurate clustering adversarially affects representation learning and vice versa. The current state-of-the-art method is a two-stage method. This method points out the problem that is affected by the initial representation. Therefore, they train using the unsupervised representation learning method to obtain good representation and then proceed with clustering. However, the two-stage method also depends on the performance of the unsupervised representation learning method. Simpler or robust unsupervised representation learning method uses instance discrimination pre-task. This method uses relations that are not suitable for semantic clustering. The key idea of our approach is this. It is to update the representation using the semantic relation obtained from the intermediate clustering result and avoid inaccurate clustering result. Specifically, there are three approaches: modified contrastive loss and confidence relation and the auxiliary embedding function. The figure is an overview of our method. Our method uses scan, a state-of-the-art two-stage approach, as a baseline and sequentially repeats the representation learning step and clustering step. In the representation learning step, we train with a modified contrastive loss that reflects the semantic relation. In the clustering step, we can utilize the auxiliary embedding function to take a well-trained feature extractor and eliminate the representation learning caused by the influence of inaccurate clustering. Then we extract the confidence relation from the clustering labels. We use this relation as a semantic relation that reflects in the modified contrastive loss in the representation learning step of the next iteration. Then we are going to explain the more detailed part of our method. This figure is the representation learning step. Firstly, we apply two different random augmentations to the images. Then we get the feature vectors of the images through the embedding function and the projection function. The embedding function is a CNN network, and in this case, we use the ResNet 18 model. The projection function consists of an MLP layers with two fully connected layers. Next, we extract the confidence relation from the clustering labels of the clustering step. For the first iteration, we assume that all images are confident and different. So in the first iteration, the first relation exists only between the images and the augmented view of the same image. Then, we concatenate the feature and confidence relations. We update the positive relation set and the negative relation set. These sets are a core part of the modified contrastive loss. We train the concatenate information with the modified contrastive loss. The main difference from previous contrastive loss is that it reflects semantic relationship with other images and does not reflect unconfident relationship in training. Next, this is a clustering step. We use the same method as scan in the clustering step. We use an auxiliary embedding function to avoid inaccurate representation learning during the clustering step. The auxiliary embedding function is just a copy of the embedding function of the representation learning step. In the clustering step, we fine-tune the embedding function to improve the clustering performance. However, even though this fine-tune process improves the clustering performance, inaccurate clustering adversely affects the representation. Like this example, if the model judges the inaccurate clustering result to be confident, the clustering labels may continue to be wrong. So even if we fine-tune the model using the auxiliary embedding function, it does not affect the embedding function of the representation learning step. In the clustering step, we find the nearest neighbor based on the well-trained features in the representation learning step. Then we train the clustering function and the auxiliary embedding function with similarity loss between the neighbor and entropy loss. After the clustering step, we also apply the same fine-tuning step as scan. This is our confidence sampling method. We obtained the confidence relation using two versions of the method. One is a single model version, the other is an ensemble model version. The single model version uses the maximum class probability to determine whether or not confident. Simply, if the maximum class probability is larger than the threshold, it is confident, otherwise it is unconfident. For the ensemble model, we use two methods. One is the ensemble voting method, which uses whether all models produce the same result or not. The other is the connection-based thresholding method, which is implemented based on the following assumption. Based on this assumption, we remove data with few connections. This method is connection-based thresholding. Next, we present our result. The first result is the performance comparison with other methods. ProFeat outperforms our state-of-the-art method in 3 datasets. ProFeat shows a significant performance improvement with a low standard deviation at the mean value. This result proves the effectiveness of our progressive feature refinement method. This is an ablation study. Iterative update, confident relation, and auxiliary embedding indicate the key idea of our progressive feature refinement method. And the connection threshold indicate the proposed ensemble method. Naive iterative learning is not enough to improve the clustering performance because of inaccurate intermediate clustering. Using only confident relation and the auxiliary embedding proves the effectiveness of our refinement approach. Also, the proposed ensemble method shows that it is more effective than the simple ensemble voting method. The next result is the graph of the clustering accuracy with respect iteration. The accuracy continuously increases as the iteration goes despite some fluctuation. Our method outperforms the baseline method within a few iterations despite the lower initial accuracy due to the randomness of initialization. This is feature space visualization using embedding function G and TSNE method. This figure shows the feature space change with respect to iteration. This change of feature space demonstrates that our progressive feature refinement successfully run representation correctly reflect the semantic classes. In this work, we propose ProFeat, a novel iterative approach to unsupervised image clustering based on progressive feature refinement. We also present an ensemble-based approach for robust confidence-based sampling. So we achieve state-of-the-art performance Our future work is the extension of our refinement method to pixel level tasks such as unsupervised segmentation. Thank you for listening.